cavity magnetron, which made radars super efficient. Cavity magnetrons are also used in microwave ovens, where they are responsible for producing high-powered microwaves. In this video, we will explore the physics behind the cavity magnetron. Cavity magnetrons work on the principle of LC oscillation. LC oscillation occurs when a charged capacitor is placed along an inductor. This simple arrangement creates back and forth motion of electrons. To find out more about oscillations, please click on the I button. When an antenna with an inductor attached to it is placed near to the inductor of an LC circuit, the antenna radiates electromagnetic waves. This is the theory behind the cavity magnetron. Obviously, the energy oscillation and associated radiation of this theoretical device will die out fast, since it loses energy in the form of radiation. How can this theoretical device be converted into a practical one? Let's look at this in the coming sessions. Consider this configuration, a cathode and a filament. The current flow through the filament will heat up the cathode, and due to this, electrons will be emitted from it. This phenomenon is known as thermionic emission. Interestingly, in this case, the electrons come back to the cathode. If we place an anode with positive potential, the emitted electrons accelerate and move towards the anode. As the theory of radiation states, the charges produce radiation when they accelerate. However, in this arrangement, the electrons radiate inefficiently as they spend very little time in the interaction space. In order to increase the time spent by the electrons in this space, a permanent magnet is introduced into the structure. The magnetic field forces the electrons to take a curved path. Since the path of the electrons is now curved, the time that the electrons spend in the interaction space is increased. The final structure thus formed is known as a Hall magnetron. Hall magnetrons are more efficient than the previously explained technology. However, its efficiency can be further improved with the help of the LC oscillations, which we saw in the beginning of this video. Let's see how we achieve oscillation in a magnetron. To achieve oscillation, the anode is designed with cavities. These cavities cause huge differences in the physics of magnetrons. To understand this, let's consider a simple case. Let's consider a metal bar with a cavity. Assume a negative charge is passing near to the metal. The negative charge will obviously repel the electrons near to it, as shown in this animation. Similarly, when the negative charge passes near to the cavity, the electrons around the cavity's surface are disturbed. You can see that an accumulation of positive and negative charges occurs across the cavity surfaces due to this disturbance. In short, the cavity surfaces acts like capacitor plates. If you connect an inductor across the cavity surface, the charges will start oscillating. This simple physics is the basis of the cavity magnetron. A magnetron has many such cavities. Many electrons are ejected from the cathode by thermionic emission. Let's track the effect of the very first electron ejected into these cavities. As explained above, this electron will induce positive and negative charges on the cavity surfaces. Here, the cavities are arranged in a circular manner. This means the charged cavity surface pair cannot stay in isolation. To keep the electric field zero in the metal, all the cavity pairs have to be charged with the opposite polarity. One interesting thing to note here is that the curved surface of the cavity acts like an inductor. This means that the charges accumulated will go for a simultaneous LC oscillation. With the help of a metal loop and an antenna, this oscillation is extracted and converted into EM waves. These oscillations will be sustained in the magnetron since the electrons continually flow from cathode to anode and transfer their energy. Now let's see what happens to the remaining electrons in the interaction space. The very first electron that reached the cavity surface has already created a charge pattern on the cavities. This means the remaining electrons will be attracted to the positive charge regions, and they will form an interesting spoke wheel pattern like this. Since the charges on the cavities are oscillating, the spoke wheel has to spin as illustrated. This phenomenon could be related to the analogy of a donkey, a carrot, and a stick. Here, no matter how many steps the donkey takes to reach the carrot always remains out of its reach. As you must have noticed, the antenna is connected only to a single cavity, since the magnetic field lines generated in one cavity also link with the other cavities. This phenomenon is called mutual coupling. This means the extraction of magnetic energy from one cavity would be the same as the extraction from all of the cavities combined. The cavity magnetron was developed in the UK during World War II to enhance radar technology. Cavity magnetrons are able to produce high-powered pulses at a shorter wavelength, and this led to the detection of smaller objects being possible. The compact size of the cavity magnetron made the radar size smaller. This UK technology was transferred to the US during World War II, and initially the US scientists had a difficult time in understanding the physics behind cavity magnetrons. Of this era